Okay, now this test lamp lighting from voltage pressure differential. Right now, we said this yesterday. How is this a? Somebody tell me how is this a pressure differential? He has a test light here, right, and he has this hooked up positive. And he had this probe in here, that connector. How is that a pressure differential? What do they mean by this? And remember, the voltmeter does the same thing. It does a pressure differential between the positive and negative lead, I said before. So what exactly do I mean by that? Does anybody remember?
It's only connected to one side of the battery.
Right. See, he's connected, this person's connected here to the positive side, right? You can see that. It's connected to the positive side, and his light is touching ground. That's a differential in pressure. When that happens, current starts to flow, and it turns that light on. So remember, pressure differential is the difference between 2 points.
Difference between 2 points, got you.
Static versus loaded resistance. Some components had drastic changes in resistance as current flows. Motors, and light bulbs. Okay. Now, I want to ask you this question here. What has to happen for current to flow?
It would be a complete circuit.
Yes, it has to be a complete circuit. Otherwise, if I had this circuit here, and now I'm missing a load, so it's still loading.
That's all.
All right. Now, obviously, that if this switch is in what position, I think somebody just said it. Mr. Garcia, you just said it, right? This switch in what position?
Open circuit.
Open circuit, right? And like Mr. Hernandez just said earlier, it has to be a complete circuit. Current has to flow in a complete circuit. I got to see a difference in pressure. All right. Oil for current to flow, it needs to see a difference in the pressure. A pressure differential.
When it's open, there's no current flow.
Say it again?
I say when it's open, there's no current flow?
Yes, exactly. When it's open, there's no current flow. I just have potential voltage. All I have right now is potential. Right here, if I check it, I would have 12 volts. On this side of the switch, if I check the potential, it's 0.
Not.
Now, once you close the switch, once I close that switch, that 0 now goes to what?
12.
12, exactly. All right, this is going to be a good example. Now, so I'm going to have 12 all the way up to this point here. Right? So it's going to be 12 all the way up to here. 12 volts. Now, with that said, so if I take a voltmeter, I can't see that. That's way too close. And go here and here. On this side, this lead
You're getting the pressure drop. I mean the voltage drop.
on this side, I would have 12. Right? You understand why, right?
Yes, sir.
Yes, it's before the load.
Right. And on the other side, after load, we're going to have what? 0,
Yeah.
right?
Yes.
0 volts. So what's the differential? 12 minus 0 is 12. And you're going to show me the difference. That's what they mean by pressure differential. You checking the pressure difference between the positive and black lead. And remember, if I lose y'all, because sometimes I go kind of fast and talk fast, especially for the people who just started, make sure you stop me so I can repeat it. Now look at this. Here's an example. Above example. We got predicted 0.250 ohms and 56 equals 56 amps. The actual is 2.5 amps, which equals 5.6 ohms. Therefore, the resistance testing is often pointless. What they mean by this statement is, you're gonna hear this term. If it ohms out good, if it ohms out bad, it's bad. If it ohms out good, that doesn't mean anything. And the reason why, because when current and heat run through something, it changes the resistance. And most of the time, you check resistance on a part, you're checking it on the bench. It's disconnected from the circuit. So, I mean, the first time I came across this, I got my butt kicked a day on this car. The customers complain about the car would cut out under load, especially towing something. And this car had spark, it had everything. Fuel, spark, everything. And it would just cut out. And I couldn't find the reason why. And I ohmed out the coils. And the coil was good. Ohmed out good. Kept cutting out. And the reason why was, to make a long story short, there was no current run through the coil when I was checking it. It's on the bench. Once you put it under heat, close the hood, right, everything changes. The resistance changes. So the car was breaking up under a load when it heated up. So ohming it out wasn't helping at all. So ohming out something ohming out a component is good if it checks out bad. But if it checks out good, don't think it's always good, because sometimes it still can be bad, especially under the hood of a car when it's heated and hot and current's running through it. Like this. Take this example. It's ohming out this wire, checking for resistance in this wire. If I check the resistance in this wire, it will ohm out perfect. But yet, that wire is bad. Right? Anybody know why?
Yeah, it's a loose connection. It's not a tight connection. It's been they put it together just by wrapping it around each other without solder or anything.
Exactly. What happens is, this is
Mickey Mouse.
But no, besides that, it is making up. Besides that, see this? It's only 2 strands.
Yeah.
What wire has 2 strands? None. It's supposed to be like this.
Supposed to be a full contact connection.
Yeah, and a whole bunch of strands too. Like that. There's no wire that has 1 strand like that. But guess what? If you ohm it out, it's going to be perfect. Because ohming something out is just checking for continuity. This right here, it just checks continuity. And that's telling you that wire has a connection. And it does. It has a connection. But like somebody just said, right? It's Mickey Mouse, or it only has 1 strand barely holding on. But this reading don't show you that. It just shows you I have a connection. And it does. It has a connection. But here's the problem. Current has to run through that wire.
Mm-hmm.
Right? All the current has to run through that 1 strand of wire. And that's going to be a problem. Let me give you an example. We talked about Ohm's law. We talked about Ohm's law, and what we did on Ohm's law actually talked about this. Remember I said before, Ohm's law is just a concept. But when we talked about Ohm's law before, it actually related to this, how to find this problem. Because imagine if this was a insulator around it. That didn't turn out good. Oh, I just tried to do make it faster. That's the insulator, right? On the wire under the hood of a car. Now, you can't see that strand of wire. All you see is the insulator. But how you find it is what we talked about yesterday. Yeah, where are these stickers? Let's call it shaky hand. All right. Okay, and what I'm going to do, I'm going to show you an example I'm talking about, that insulator. This is a hold on. This is a connector right there. All right. Yeah, blue line's a connector. Okay, this is a good circuit.
Hey, mute your cameras, please.
This is a good circuit. Okay. Now, in a good circuit, we're missing what? And is this a series circuit or parallel circuit?
Serious.
Series circuit, exactly. And I got 3 dBohms.
We need the amperage.
Voltmeter here. And a voltmeter there. Alright. Now, DBOM means digital volt ohmmeter. You might hear the term DMM also, as digital multimeter. Now, in this circuit, as you see here, in this series circuit, like Mr. Garcia just said, how many amps in this circuit?
4.
4 amps. You know, I actually got that wrong. I said 3 in my head. You're right, it was 4.
3 ohms, 4 amps.
Yeah, it's 4.
The
4 amps in this circuit. Now, what's the rule of amperage in the series circuit?
Stays the same.
It stays the same, right? Remember, amperage leaves the battery does it to do a job. It's going to go through that bulb, heat up the filament, the light's going to come on and return back to the battery.
So,
And what's the pressure? Sorry, I just had to answer. What pushes what's the purpose of the voltage?
to push the current.
Right. Its job is to push the current amps through that resistor, which is the bulb here. So exactly right. So if everything is good, and I have a good circuit like I have here, you have a good circuit, right? According to Ohm's law, that one light, say this is a headlight or brake light, I'm expecting to drop what? Now let's do the math. Remember, the math is a concept to an actual application. But let's do the math on it. How do we get voltage in Ohm's law? Amps. What is it? Amps times what?
Resistance.
Resistance. I keep switching up on y'all.
12 volts.
Amps times resistance. Remember, I used to put an A. It's the same thing. That's how I learned it. That's why I keep doing that. But actually, every book says I for intensity and R or omega sign for resistance or impedance. So we got 4 amps times 3 ohms.
So,
Right? Exactly. 12 volts. So I'm thinking, I got my voltmeter, I'm on this bulb, it should drop 12 volts. Right? According to the rule, it should drop 12 volts. Now if I'm checking for my potential voltage on a good circuit, and this box here, I have what?
12 volts.
12 volts.
12 volts. Right? Let me add another box here. Now I put another voltmeter here to check for potential voltage. Also, I'm gonna have what?
12 volts.
12 volts again. Right? All potential voltage leading up to the bulb. Now, since I got 12 volts going up here to the bulb, right, and it's used up 12 volts here, how much is on the ground side?
Close to 0.
Right, close to 0.
Near 0.
Near 0. All right, 0.1 or less. Well, I mean about 0.1 or less. It could be
0.01.
Yeah, exactly. 0.01 also. Same thing. As long as it's less than 0.1. Alright. So now look at the pressure differential. I had 12 on this lead, 0 on this lead. Now voltmeter is going to show me the difference, which is 12. But let's do this now. We all know that's a connector right there. Let's say that connector has resistance on it. And like I said, you can't measure resistance like that, but you can find another way I'm about to show you. Let's say for this example that it has resistance in it. Oops. 3 ohms. What's the amperage now?
2.
2. Because the first thing he did was add up the resistors, which is 6. Okay. Now it's 12 divided by 6 equals 2. It's 12 volts divided by 6 ohms equals 2 amps. So we just took our, that's wrong. We just took our 2 amps and sent it down to, 4 amps and sent it down to 2 amps. But the whole circuit now just changed. We don't have a good circuit anymore. We have a bad circuit now. Our resistance went up and current went down. Remember we said before that teeter-totters, as resistance goes up, current goes down. But now, it's going to affect the bulb now. Let's say there's a light bulb in the car. It's going to affect this bulb now. Oops, shoot. So now we got 2 amps in the circuit. Now with that said, now imagine that I'm going to the light bulb of your car, or brake lights, or headlights, and I expect to see 12 volts. I go across it, and I see, according to this math, I'm going to see what? I want to take the resistance here and the amperage to find the voltage drop. Remember, to get the voltage, to get this, we had to do amperage times voltage. 6. Now here's the thing. You don't do this math on the car at all, right? You don't do the math on the car. The math is a constant, remember? But I know I got a 12 to 14 volt battery. I go check the voltage to the light bulb. I look at the wiring diagram. You're expected to see 12 volts. But you go to the car, you got 6 volts. Now in your head, your third eye, you know something's wrong. Automatically now you know something's wrong because you see 6 volts. You didn't do the math. You didn't get no pencil and paper out. You just put the meter across the light. Now you see 6 volts. You say, uh-oh, something's wrong. All right? And you don't see all this. You don't see that. All right? Because remember, we're here. All you're seeing is a connector, some wires, some bulbs, and grounds. You don't know the problem, man. So now, to find a problem, we do something called a voltage drop. All right, we do a voltage drop. We see our connector, we see our wire diagram, we see a connector. Let's check the voltage on the connector. All right, we go across this connector. Well, it's 3 ohms, right? And we see 6 volts. Remember, 3 ohms times 2 amps equals a 6 volt drop. And that's what's taking up the 6 volts. Now that's what's taking up the other 6 volts when it's supposed to be 12 in the bulb. Now, here's a $1 million question. Now, I told you before, I love this term. If you really understand that term, you understand why it's like that. Why you see 6 volts across that connector. Why is it 6 volts across that connector?
Because there's a false connection of corrosion or false trap.
That's exactly right? But I want it more of a, really picky. That one term I like to hear all the time, like I told y'all.
There's not enough power. What was the word you said it last week?
Pressure differential.
Pressure differential.
Well, that's exactly right too. There is a pressure differential, but that's not what I'm looking for though. But you're right though. There's a pressure differential there.
It's not a complete circuit.
Somebody say something?
It's not a complete circuit.
No, it has to be complete circuit. You got amperage, remember? An incomplete circuit wouldn't have amperage.
Yeah.
Where that insulator's at, there's a false contact.
Yeah, you're right. Why is it 6 volts there? And it's supposed to be 0. Across any connector, you're supposed to have less than 0.2 volts. And I got 6.
Connection.
Huh?
Because there's an incorrect connection.
That's correct also. But why?
Because
What's that term? What's that term? Why is the 6? My question is, why is the 6 volts there though?
He used that term Wednesday.
I use it all the time.
Because the bulb is taking the 6, and so the other 6, that's where it goes.
Yeah, that's right.
Oh, but there's a key word he always says.
You want me to tell you?
Yeah.
Is it a bad ground or a bad circuit?
And not on the ground side, on the feed side.
No, it's the word the term he uses. What is it?
Hey, Robert, you remember? Are you there?
I'm here.
Did you think of anything?
That have something to do with number ones?
Yeah, you're close. That's close. One's in the phrase.
We need 1 volt
1 volt to push 1 watt to push
through 1 ohm of resistance.
Ding, 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 y'all got it. There y'all go. It takes 1 volt to push 1 amp to 1 ohm resistor. And the reason that the 6 volts is there, because you have resistance, and it's taking up 6, it's going to take, gotta pick that up. It's going to take 6 volts of pressure to push the current through that resistor. That's why you have 6 volts there. So I got to get the 6 volts from somewhere, so it's going to take it from the bulb. So it takes that 6 volts of pressure to push the current through that resistor. That just gives me goosebumps saying that. I don't know why I like that phrase.
So now the second square going on the bottom.
So yeah, so now
volts.
So now let's do this. So now does this one stay at 12 volts?
Yes,
yes it does.
Yes.
How about this one?
No, that's 6 volts.
That's 6 volts. Now Garcia said this earlier on his. I have, like you said, on this line right here, I had 12 volts. Right? I had 12 volts on that side, right? On this side, I had 6 volts. What's the differential from that? 6.
6.
That's how the voltmeter check pressure differential, or the pressure difference. It's going to show you the difference between the 2 leads. So now we got 6 coming out. So now we only have 6 for the actual load. So now if that light bulb, so what happens to the light bulb now? Is it bright, dim? Does it still work? The same or what?
It's dimmer.
It's going to be dimmer now. Now, how about the ground? The ground has no effect in this case. It's still 0.1 or less. Because the problem is not on the ground side. Now, with all that said, anybody, before I erase all this, I need to erase it to get back to where we started at. With all that said, anybody have any questions if I erase this? Because I don't know how you... Can I move that? I don't know how you move this. No question, right? So with all that said,
This is
That
so
can't be moved.
we have a bad circuit. You said right there. It's a bad switch right now.
we got a bad connector. This connector is bad. This right here, that's a good question. I should have said that. This voltage drop here across this connector.
So it's bad because there is resistance in
Yes,
there, right?
across that connector is bad because of resistance. Right, I should have said that. You're exactly right. That connector is bad. That connector should never drop 6 volts. I think it's 2. I'm pretty sure. I think it's 0.2 or less. Should never be should never be that high. Right, so that connector is bad. But the point
Mr. Davis,
Yes.
why do we have a connector there?
oh, that's how you plug everything in. Remember, all wire is not wire to wire. Sometimes you got a wire going to a connector, to a male and female connector, to a wire to the load. That's how you plug things in on cars. You use connectors.
Got it. Thank you.
That's a good question. Now with all that mess I just wrote on this board here, if you can remember that, we're going back to the original statement. I'm gonna erase all of that. I wish I could find a way I just can.
Is this going to be on the test?
Oh, I just asked you 4 questions on the test. we just have about 4 questions on the test. And you want to know something, Robert? You just asked the questions on the test.
Okay. So, guys, write it down.
What was it, Robert?
Well, if he's going to play it back, you'll hear it. Mr. Nate, you're recording this, right?
Let me check. Yes, it's right. It's recording.
Good.
That's recording.
Gabriel, check the recording later.
All right, now remember we started from this. I swear I don't know how to get this game done. I wish I knew how to get this.
Ask Gabriel. He might.
Try right-clicking on the sticker, Mr. Nate. See if you
I
can
tried
click
that already.
Or when you get the down delete, hit delete.
Hold on, I think I just figured it out. I got it.
Now they're drawing you.
All right, so now we started here, right? This is where we started from. This is an insulator. And keep in mind that, like I said, you can't see that. Or you can't see that strand of wire. All right, there's no way you can see that strand of wire. So what you're gonna do is how you find it. And go to this side of the connector and this side of the connector. If I read 6 volts, you know you have a problem. Remember, if I remember this correctly, I have to double check. It's 2 volts or less, 0.2 of a volt or less. Now, was that totally confusing? Do y'all see the relationship? Because remember you cannot see that strand of wire. So remember, you can't see this. How you gonna find it? You do something called a voltage drop. But if you ohm it out, it's gonna ohm out good. Remember, we got billions of current running through this wire. All you're gonna do is have a real serious problem right there. Heat up and cause resistance. And it's supposed to be like this, not one strand like that. Now, did I totally confuse you on that, or did you understand the relationship between that drawn and this?
10-4.
Because remember, I didn't notice that, but remember, this is the insulation right there. Right, that's the insulation. All you're gonna see is this insulation here. That's all you're gonna see is that. You're not gonna see the wire at all. I actually seen this happen on a car like Jeep that wouldn't start. The thick battery cable, and how you could tell is the cable was nice and red, right? But that one spot was broken at internally. You could see it's like white, weak. You feel it. It feels just weak when you twist it, but you don't see it initially. All right, next one, testing voltage drop across a single strand. Oh, we just did that, didn't we? I guess I didn't have to do all that drawing, huh? I think my work there. So he's doing right here. This is what I just drew. He's testing the wire, the insulation. He, they testing that wire. The same thing I just drew earlier. Testing the voltage drop across a single strand of wire, but this time we're testing the ground circuit. Now, is this here parallel or series now?
Parallel.
Yes, that's parallel. That's a parallel circuit. Any questions?
What would happen if the light bulb and toggle just won't go out?
I'm sorry, say it again?
There's a question, I know the answer, but it's just a question so anybody could understand. What happens if one of the light bulbs went out?
Oh, and this one? That's a good question. I'm sorry. I'm just saying, playing with this. I'm trying to figure out how I can get that selection back here again. Yeah. Anyway, his question was, right? If one of these light bulbs go out, will it affect the other circuit? Remember we talked about this yesterday, the Christmas tree light bulbs, right?
Yes.
Now,
The other, yeah.
No.
I'm sorry, Robert. What you say?
I said if one goes out, the others one stay on.
Right. Exactly. You're exactly right. If this one blows out, this one still works. That's okay. And remember, in a parallel circuit, there's more than one path to ground. You have this way, the Benjamin Franklin way, positive and negative, and you got this way. Got more than one path to ground.
What about they were side by side?
And let me ask you this one. Let me ask you this. I said this earlier, so y'all remember it. What's the flow this way called? Like good old Benjamin Franklin, when he first discovered electricity? What's the flow of electrons called in that direction? From positive to negative.
What was that, Mario?
Is that a conventional
Exactly. Who's that? Angel? Who's
Mario.
that? Mario. Exactly. Right? Positive. That's conventional. Negative, the positive, which is this way, it's called, anybody remember? Yeah, hint. So this is conventional. The other one is called electron flow. Does it really matter? No, not really. There's just two different scientists debating. We usually check everything conventional, positive and negative. But there's sometimes you want to go negative, positive.
Mr. Nate,
Yes.
you know how you said earlier we were Tuesday we were talking about the Christmas lights on Monday?
Yeah.
What about those light bulbs were side by side and one blows out?
And this one?
Yeah.
He's talking about a series circuit. Right, that's a series circuit. If God, you suck.
Did they make a series circuit parallel?
Oh, you suck. Hold on, I gotta do it again. This is a series circuit when they fall on one path to ground. Okay, that's a series circuit when one path to ground. Now, if one light goes out on this one, guess what? Will it affect this light also? Will it affect this one?
Yes.
Yes, it will. They both go out because current has nowhere to flow now. There's only one path. So
But
both lights.
how about the, like, for example, we're going to put in another example of Christmas lights. They're serious because they're next to each other. But nowadays you see that one blows out, they still stay on.
Yeah, some are still like that, but I had seen some that weren't like that anymore.
Could a series circuit be parallel too?
Yeah, you talking about this now. You talking about a series parallel circuit. Alright. Now, if this one blows out, this one and this one will still work. Alright, but if this one blows out by itself, they both stop working. Everything stopped working because that's in series. Anything in parallel stop working, other ones keep working. But anything in series to it, if that goes out, it affects both circuits.
And I'm asking those questions because I think there's new guys that could ask these questions, but they don't ask it because they're nervous or something. Because we already went through this, so we already know.
Okay, y'all asked very good questions today. We're going to stop it. I got a meeting at 11:10.